Welcome back. We now will be looking at an example where we find the distance from a given point to a given plane. So let's say that I have a plane and the plane has normal vector n, so n is perpendicular to the plane, and P is a point on the plane, and Q is a point that's not on the plane, possibly. So we want to find the distance from Q to the plane. So what do we mean by the distance from the point Q to the plane? Well, we mean the perpendicular distance, right? So from the point Q, if I make a perpendicular line onto the plane, then I get the point Q prime, and the distance then from Q to the plane is the length of Q prime. So the distance is the length Q prime. How do I find that? Well, P is a point on the plane, and Q is this point. So if I look at the vector from P to Q, and then at the point P, if I draw the normal vector n to the plane, then notice that if I look at the from the point Q, if I make a vertical line onto n, then the vector from here to here, the red vector, that's the projection of the vector PQ onto n. Well, clearly the length of this projection vector would be the same as the length QQ prime. So the distance from Q to the plane can also be found by finding the length of the projection vector of the vector from P to Q onto the vector n. So the distance from Q to the plane is equal to the absolute value of the component of the vector PQ onto the vector n, because this is the length of the projection of the vector PQ onto the vector n. Okay, so let's say we want to find the distance from the point let's say we want to find the distance between the point Q, which is with coordinates 1, -2, 4, to the plane 3x plus 2y plus 6z is equal to 8. How do we find that distance? Well, the distance is so the distance to find the distance from this point to the plane, what we're going to do is we will first find a point on the plane. So how do we find one point on this plane? Well, we will set two of the variables to whatever value you like, and then we can solve for the other. So we are going to set x and z to 0, and then we will solve for y. And if we do that, we get y to be 4. So 0, 4, 0 is a point on the plane. So I'm labeling that P. Again, I don't have to pick 0, 0 for x and z. I could have picked other values, but those are convenient values to pick here because that will be easy to, then it'll be easy to solve for y. Now, what would be a normal vector to the plane? Well, a normal vector to the plane would be given by the coefficients of x, y, and z here, so 3, 2, and 6. So this is a normal vector to the plane. This is a point on the plane. So then let's look at the vector from P to Q. So here P is a point on the plane, Q is the given point from which we are trying to find the distance to the plane. So if we look at the vector PQ, then we get so from Q we subtract P. So So it'll be 1, minus 6, and 4. So this would be the vector from P to Q. Again, the vector from P to Q would be Q minus P. And so now we know that the distance will be the component of PQ along the normal vector n. So the distance would be the component of PQ along the vector n in absolute value. So the component we know is the dot product of PQ with n divided by the length of n. And then the dot product here would be 3 times 1 is 3, minus 12 plus 24 divided by the length of n would be 3 squared plus 2 squared plus 6 squared, and then the square root of that. We get 15 out from the numerator here, and then root of 49 in the denominator. Root of 49 is 7, so we get 15 over 7 at the end. So the distance between the point 1, negative 2, and 4 and the plane 3x plus 2y plus 6z is equal to 8 is 15 over 7. Okay, so this is it. This is the end of my discussion on equations of lines and planes. Thank you for watching. I will be seeing you in the next module.